Okay. All right. So this is be the third part of our discussion of chapter 4. And what we're going to do right now is we're going to start looking at the ways that we'll use F equals ma to actually analyze motion problems. Okay. And we're going to start with a thing called free body diagrams. So free body diagrams are just a graphical tool. It's a way to inventory the forces on it. So in order to correctly know how a body moves, we need to know what the net force on it, which means that we have to identify all of the forces that are acting on a body. Okay, and if we want to know how the body moves, it's going to move according to the net force that's on it. If we don't identify all of the forces that are on it and we miss one of them, then we will not be calculating, we will not want to get the proper answer for the motion of the object. And so this free body diagram, these free body diagrams become very important in this process because they're the way for us to examine an object and to determine what in fact is happening to the body and is causing it to move. Okay, so again, we do this with a free body diagram. A free body diagram is very simple thing. You guys have seen me draw it in class. If I were to draw myself, and I think I've drawn pictures of myself on the board, I've drawn myself as a square. You can use a point or a circle or anything, but just make some sort of an object. And then what you do is you look at that object, and this is the physics part of this now, is you have to look at the problem that you're trying to solve, and you have to determine what forces that you think are on it. You have to draw all of those forces on that object, forces that act on the object, and I've underlined on the object in this slide for a very specific reason, and we'll talk about that in just a moment. You need to look at the forces, and you need to show each one as an arrow that's pointing in an appropriate direction. So that's the way we start these problems. We start them with free body diagrams. One of the forces that we'll almost always have, not every problem, but most problems will have the weight or the gravitational force on it. And so we'll draw a picture, and then we'll have some orientation of that free body diagram. We'll know how that body's oriented with respect to the ground. And the vector force of gravity will be pointing towards the center of the Earth. So the object will have to be, it'll have to be understood how the body is actually, what the relationship of the body is to the Earth. Okay, so we're going to do a lot of free body diagrams. I'm going to start doing these in Chapter 5, but this is the way that we start every problem using F equals ma, okay? So here's the process. We draw a free body diagram of the object. Okay, this means that we, like just what I said before, we got to identify all of the forces. We've got to figure out, what their direction is. We need to know the forces somehow. Okay, we have to, once we have the forces drawn in vector as an arrow diagram on the free body diagram, what we're going to do is we're going to choose an appropriate Cartesian coordinate system. We need a Cartesian coordinate system because we're going to have to add vectors up, and we need to do that within a coordinate system. Okay, and the coordinate system, of course, is your coordinate system. You pick any one you want. You'll hopefully pick one that makes the problem easy to solve. And usually, in most cases, if we know the direction of the acceleration, we have some information about the acceleration, and we know that, it's got to be going parallel to an object, or it's got to be going up or down or something. We'll usually choose that direction, the direction of the acceleration, to be the direction of one of the major axes, either the x or y or z axis. Okay, that will be a hint, but again, the coordinate system is up to us to decide how we want to do it. And by the way, you can pick any coordinate system you want, and if you use it properly, you can get the same answer independent of the coordinate system. The universe doesn't care. The object's going to do what it's going to do. The coordinate system is for us in order to be able to do quantitative analysis. Okay. So once we've got the coordinate system, then what we do is we're going to use that coordinate system to sum the forces to get the net force. Okay, and what we do in general is we'll write down each one of the forces in the Cartesian unit vector notation, and then we'll sum them up, because once we have our forces in the Cartesian unit vector notation, it's very easy to sum them up and get a net force. Okay, and once we have the net force, and you know, in our case, it'll usually be two-dimension. It'll be it'll have a force that has a net force that has an x component and a y component to it. Once we have that, then what we do is we set that force, this force right up here, which is a vector, equal to the mass of the object times an acceleration vector. Okay, and what that does, this is a vector equation now, and what we do with a vector equation, of course, as we talked about early on in the course, early on is, it wasn't that long ago, but at any rate, the beginning of the course when we talked about vectors, and we know that for this vector equation to have an equality here, for this to be truly an equality, the x component of this net force has to be equal to the mass times the x component of the acceleration. That's this right here. And likewise for the y components. They have to be equal. So what we do is we decompose this vector equation into two scalar equations. These are just numbers now. These are components. Okay, these are real numbers in here. And so what we'll in general, what we'll get from F equals ma is we'll get two equations, and we have to solve them, and we'll solve them simultaneously. These actually will be solved independent of each other, because the motion in the x direction is decoupled from the motion in the y direction. We've already talked about that. And so this equation here will describe the motion of the object in the x direction. This one will describe the motion of the object in the y direction. Okay, so now to go forward with this, what we'll do is we'll take any knowledge that we have of the acceleration, and you know, sometimes we know one of the components is 0. When I'm sliding down a ramp, I know I'm not going into the ramp or out of the ramp, so I know the acceleration is 0 in that direction. And what we'll do is we'll apply that to the equation, the F equals ma equations. We'll do that a lot, okay? And once we do that, then what we can do is we can solve for the acceleration to get the motion. Sometimes we'll be solving the equations, we'll know the acceleration, we'll be solving it to get the forces that are causing the acceleration. This is how we're going to proceed with solving F equals ma problems. So what I've done, I know that I've done this for you guys already, but we've talked about the example of a freely falling mass, just a book falling in gravity. I'm going to do that again. I'm going to do it on a video, and you guys can take a look at it. And I'll go through this process that we just discussed through each step, and I'm going to go through chapter 5, and we're going to solve a lot of force problems using F equals ma. And I'm going to try to be very rigorous about using the steps that we talked about on the last slide. Okay, I'll try to be very careful about that. Okay, so finally, the last topic in chapter 4 that I want to discuss is I want to discuss Newton's third law. So we've talked about Newton's first law, which in a large sense is a special case of his second law. His first law, Newton's first law, as you know, says that if you don't interact with an object, if the net forces are 0, that would be no interaction with the object with its environment. If the net forces on an object are 0, then its velocity is constant, the acceleration is 0. Newton's second law is your F equals ma, which we've just talked about. And Newton actually gave us a third law, which is a fairly important law. It's a very important law, actually. It's the basis of a very important conservation law in the universe. And simply, Newton's third law states that forces always come in pairs. Okay, if you have a force on an object, if an object experiences a force, that force is coming from somewhere, and it's coming from so the forces are an interaction between two objects, and it's a reciprocal interaction. And what I mean by that is if object 1 applies a force to object 2, so here's object 1, and it's applying this force to object 2. Now, this happens to be a long-range force. These guys aren't touching, but this could be an electromagnetic force. It can't be a gravitational force because I've shown the arrowhead, the force on 2 is actually pushing it away from 1. So I know this is not a gravitational force. But it could be the electrostatic force between two charges, two positive charges, for example. It's a repulsive force. But if object 1 applies this force, the force on, read this as the force on object 2 due to object 1, so it's F21. If that is occurring if object 1 is applying a force to object 2, then at the same time, object 2 has to be applying an equal and oppositely directed force, F12, on object 1. So this is the force on object 1, due to object 2. And these forces are equal in magnitude, and they are pointing in exactly the opposite directions. So this completes Newton's set of laws. He's got 3 laws. And now what we'll do is we'll spend some time actually figuring out how to apply them. That will be the subject of chapter 5, which I'm going to give you, I'm going to record that momentarily. I will have a couple of videos associated with chapter 4, but we're really going to get into the quantitative part of this in chapter 5. So you guys need to read your chapters 4 and 5. I know you're doing that. Do the homework that's in them. And then what I will do is I will hopefully see you all virtually here in office hours. I do want to tell you that at some point here, probably it might be Thursday, that we will try to get together virtually through a conference. So we should, all of us should tag up together as a group over the internet. So anyway, good luck, and I miss you guys, and I'll talk to you later.